Let me thank Miranda House and Ramanujam College for inviting me to give this lecture series, which is supposed to be in 3 parts of half an hour each. Uh, Let me first share the slides. I hope my screen is visible. So the lecture is on, the 3-part lecture is on nanomaterials and its applications. And as all of you know, the subject of nanomaterials has been of great interest all across the globe, uh, uh, starting from school, college, university to research laboratories. Everybody has been talking of nanomaterials over the last 20 years. And I will be touching upon the various types of nanomaterials, its origin, and the techniques by which we characterize nanomaterials, and then what are some of the applications of nanomaterials which has made it so important in the world today. So if you want to talk about nanomaterials, first you must know what is materials. So as you see, there are many types of materials all around us. There are natural materials and there are man-made materials. So in natural materials, you can see these are crystals of garnet, which is a kind of an oxide, and there are various types of garnets. Similarly, there is quartz or gold or marble. Many of them occur in nature, in mines and in mountains. Many places under the sea also you find many materials, and these are naturally occurring materials which are formed through geological processes and chemical reactions occurring at high pressure, high temperature inside the earth and in the presence of water and other gases. There are man-made materials like cement or this CD, this IC chip. Many of them are made in industries by a human being and has developed as our understanding of science and technology has developed. Now, one thing in all these materials, whether it is man-made or it is natural, uh, they are made of some material. They are made of a compound or a mixture of compounds. And these compounds, mixture of compounds, have some particles. And these particles have some size. Normally, this size of a particle which we can see with our eyes is around 0.03 millimeter or above. That means if you have particles which are smaller than 0.03 millimeters, you will not be able to see those things. Nanomaterials come under that regime. They are much smaller than 0.03 millimeters. As all of you know, the definition of 1 nanometer is 10 to the power minus 9 meter. So it's much smaller than 0.03 millimeter. So we will certainly not see those particles with our naked eye. So that is one thing I wanted to tell you. What is the connection between materials which we see around us and nanomaterials? So clearly nanomaterials cannot be seen with our eyes. So you need techniques or technology which can act like our eyes, and then we can observe them. If you want to see particles which are smaller than 0.03 millimeters, we sometimes use microscopes. And depending on the size of the particle we want to see, we have to use different types of microscopes. Right? In high school biology labs, you might be using optical microscopes to see some objects. Optical microscopes use visible range, the normal natural light, and it is reflected by lenses or mirrors onto your object. And you can see some of them, but they are large sized. They are not as small as nanoparticles. If you want to see small particles like shown here, these are grains within a material. of size of around 20, 30, 40 nanometers, then you have to use what is called a scanning electron microscope. So if we look inside any solid, say you have a table, if you want to look on inside that wood in the table, or you have a metal sheet, if you want to look inside the metal sheet, then you will need such scanning electron microscopes or other types of microscope which can show the grains inside those sheets of metals or a solid or inside a wood piece or plastic piece, any material that you see with your eyes, you can look inside them with much powerful microscopes like scanning electron microscopes. And normally, with traditional scanning electron microscopes 20, 30 years back, we could observe something like 100 nanometers, etc. But today's scanning electron microscope can give you a resolution of 1 nanometer also. Okay, so you can see even 1 nanometer with the world's latest scanning electron microscopes. And of course, there are other microscopes which are much more powerful. Okay, so these are some of the type of grains which you will see, spherical grains with some voids or grains which are interconnected, very faceted grains. That means you can see sharp edges. Many of these depend on the type of material that you are seeing and observing under the microscope. This right side figure is, of course, a drawing which is trying to tell you, like in a textbook, that these are spheres which are uniform, and in nature they may not be uniform. They may be more like this, which are not very uniform. They may have voids, etc. Much smaller than these particles are, of course, atoms, and these are textbook examples where atoms are drawn, but this is not a real picture of the atom. Okay, these are drawings. Now, atoms are smaller than nanometers. One atom, the diameter of an atom is 0.1 to 0.2 nanometers, right? If you take any crystal like a sugar cube, a small speck of sugar will have, which will be like a small crystal, will have 10 to the power 21 atoms. And it will have a three-dimensional structure. But each atom is much smaller than 1 nanometer. So it is like 1 angstrom or 2 angstrom. Okay, typically these are the diameters of atoms are like that, 2 angstrom, 3 angstrom. And this is smaller than nanometer. That means your atoms are smaller than 1 nanometer. 1 nanometer is 10 angstrom. Okay. So if you now put a length scale, if I want to have a scale of different sizes, you can see that the nanoscale, which is 1 nanometer, is here, 10 to the power minus 9 meter, and typically up till 100 nanometers, that is 10 to the power minus 7 meter. This is the range that is called the nanomaterial range. This is kind of a qualitative definition which goes around in the world of nanomaterials, nanoscience, nanotechnology. Every scientist in the world kind of works in that area and calls it nanoscience, but there is no real reason why 105 nanometers cannot be nanoparticle. You understand? This is a very loose definition of nanoparticle, should be between 1 nanometer to 100 nanometer. In certain applications, especially in biology, scientists work even with 200 nanometer particles, 300 nanometer particles. So it depends on the area of interest, whether you have one nano, you are working with 2 nanometers or 3 nanometers and looking at some applications, or you are working with 100 nanometers, 150 nanometers, you may have different applications. Okay, but in general, all the loose definition of nanometers or nanoscience exists is between 1 nanometer and 100 nanometer. That is the scale we are focusing. And loosely, it is also called mesoscopic range. if it is smaller than microns. So we have a macro size range, which is in microns and above. So if you have 1 micron, 1 millimeter, this range, or 1 meter, this is called the macro size. Less than 1 micron to this nanometer, this is all, it's called mesoscopic, within which 1 nanometer to 100 nanometer is the nanometer or nano science and technology works there. Smaller than 1 nanometer, that is like an atom, or even inside the atom, which is the nucleus, is femtometer. So this is much smaller. So this is not in the purview of nanoscience and technology. This becomes different science. And this is a very good topic or advanced topic of research where scientists work in femtoseconds time scale or femtometers dimensions. There are physicists working in this area within the nucleus, etc. Today's latest is in the world of astrophysics, where 10 to the power minus 18 meters people are talking. But coming back to nano size and nanometer and nanotechnology, this is the range in which people work between 1 nanometer to 100 nanometer. But it does not mean that there is nothing happening below 1 nanometer. There is a lot of science and technology happening below 1 nanometer also. So, like if you now giving you a perspective, if you look at your hand with your eyes, you will see certain lines, okay? And those lines will have maybe thickness. You can see these widths, maybe 1 millimeter or something, and you are looking at an area of 1 centimeter. If you zoom more closely, the lines in your palm, in your hand, will look like trenches. And for this, you need to have a microscope. So from your natural eye, you go to an optical microscope or something, then you will start seeing some trenches. If you use electron microscope, which are much more powerful, then you will start seeing objects which are in the order of microns now. This is a white blood cell within your palm. If you go further, zoom further, using more powerful microscopes, you will start seeing DNA, and then you will start seeing atoms. So very powerful electron microscopes, which are called transmission electron microscopes, you can see even atoms very easily. Okay? So all this is there. Only which eyes are you using to see, you will see different things. So if you are using a certain eye, which means our natural eye, you will see something. If you use an optical eye with mirrors and all to focus the light, then you can get an optical or light microscope. You will see something else. If you use electron microscope of some kind like the SEM, you will see something. If you use more advanced electron microscopes, you will go and you will be seeing atoms also. Now this nanoscale, to give you an idea of what is this nanoscale, how should I think about it? So if you look at a football, which has a diameter of around 22 centimeters, and if you look at the earth, so compare a football, which all of you have seen, and the earth, then the football is 10 million times smaller. So you can understand the football in your hand is 10 million times smaller than the earth. Similarly, now if I talk of a nanoparticle, which is a carbon C60 molecule, it's a fullerene whose diameter is less than 1 nanometer. So you can take around 1 nanometer, it's actually 0.7 nanometer. If you take the ratio of the football and this 1 nanoparticle, it is 1 billion times smaller. That means now you understand that how big is the earth in terms of the football. The football is much, much bigger than that, than 1 nanoparticle of C60 molecule. So you can understand how small is 1 nanoparticle by this analysis. Nanoparticles exist all across from living things to non-living things. That is one thing. And from the nano world, we can go, as I said, to the micron world. From the nano world, we can go to the micron world. And from the micron world, we can go to the macro world. That means where objects are measured in millimeters, meters, so much bigger than 1 micron, which is 0.001 millimeter is 1 micron. So if you are above that, you are in the in millimeters and above, you are in macro world. In micro world, you are between 1 micron to say 0.1 millimeter. And then below that, you have the nano world till 1 nanometer. Okay. And these different length scales, because they correspond to some lengths, as you see, nanometer is 10 minus 9, we have 10 minus 8, minus 7. So these are lengths, right? And you can have rays corresponding to these lengths. So wavelengths of electromagnetic radiation corresponding to these numbers will give you different type of rays with which you are familiar. So you are familiar with ultraviolet rays, which are having wavelength in this dimensions. You have visible rays having larger wavelength. You have infrared, even larger. And when you go to millimeter wave, that means wavelengths are in millimeters, you are in the microwave region. So these are also called millimeter waves, which are microwaves, which are used for satellite communication, etc. But in the nano world, you are below UV or much below UV, right? Now, various objects exist, as you can see. A DNA, a single turn of DNA is 2.5 angstrom, which is 0.25 nanometer. So one turn of DNA that in the helix is around 0.25, less than 1 nanometer. Of course, DNA itself is very long. It can be meters. But one turn of the DNA is around 0.25 nanometer. Objects like carbon nanotubes have diameter of around 2 nanometers. You can have atoms which are arranged in the form of a coral, like in a stadium. So this is a very famous picture of a copper surface. That means a sheet of copper made of copper atoms. And on one particular face of that, the 111 face of copper crystal, if you put iron atoms, so this is a very famous work where 48 iron atoms were put on a sheet of copper surface and arranged in a manner such that you will have, you can arrange this by what is called an STM tip. So which I will come to that. So you can exactly position 48 iron atoms in this manner. And these give rise to nanotechnology and many other phenomena. You can have electronics at the nanoscale. This is a transistor, which you study in physics. At the nanoscale, this width is around 60 nanometer. You can make gears, many machines. Your cycle has a gear, you will have gears in cars and other vehicles. You can make gears in micron size, and that's called micro electromechanical devices. This was known 20, 25 years back. People made using some technology, very small gears. Today, you can use nanotechnology to make even smaller gears. So these are man-made machines. Very important in nature and for medicine and drug delivery is some objects which occur naturally and we can also make in our lab, which are called liposomes. Liposomes have this double layered vesicular structure where these molecules are, in chemistry we call them surfactant type molecules. They have a head group and a tail, and these form a bilayer, and inside these kind of vesicles there is a volume where molecules or drugs are encapsulated. And these are naturally occurring also and man-made liposomes can also be made. And these have sizes which are small. They can be of 100 nanometer size, 80 nanometer size, 200 nanometer. So liposomes can be of that range, and you can use them for drug delivery, etc. For example, one of the latest vaccines in the world, which uses the mRNA technique, the Pfizer vaccine, is a very, very powerful vaccine for COVID-19, uses a liposome for delivery where the mRNA is actually inside the liposome. And when it is injected, it is delivered inside the body. These kind of structures are very important and interesting for medicine and have sizes in the nanometer size range, but they are not 5, 10 nanometers, they are in hundreds of nanometer size. You can see here that water molecule is like, zero point 0.1, close to 1 nanometer or zero point 0.1 nanometer. But a cluster of molecules, say 100 molecules, will be 1 nanometer or something like that. So as you go about increasing, you have various objects. An antibody has a size of around 10 nanometers. A virus has a size of around 100 nanometers. Bacterial cell has a size of 1,000 nanometers. So a lot of living things are also having nanoscale. And liposomes are very important in bio-nanotechnology. You can make many types of nanostructured materials or nanoscale materials. Nanoscale materials means at least the material that you are making, one of the dimensions has to be less than 100 nanometers. So if you see these are gold nanoparticles, these appear to be spherical, and the diameter of these nanoparticles are probably 5 nanometers, etc. Here you can see silver triangles. So these triangular edges can be of few nanometers. So then they will be called nanoparticles, nanoscale structures. This I already discussed, where on a copper surface, you have 48 iron atoms arranged in a pattern using a technology, using a machine which is called a scanning tunneling microscope, which can put one atom by one atom on top of the surface, and you can create this kind of what is called a quantum coral. And it is a nanostructure or a nanoscale. It can be called a nanoscale material. Similarly, this is like a flower-like structure. But this flower-like structure you cannot see with your eyes. None of these you can see with your eyes. These flowers you are seeing through a microscope, electron microscope. So the dimension of these petal-like things is maybe 3 nanometers, 5 nanometers. So nanoscale materials, one of the dimensions has to be less than 100 nanometers or close to 100 nanometers. The other two dimensions, that means if you have a long wire, which is like 1 meter long, can still be a nanoscale material if its diameter is 100 nanometers or less. The length can be 1 meter also. Still, it will be called a nanoscale material because one of its dimensions is less than 100 nanometers. So that is why we call all such objects which has one feature size less than 100 nanometers in a device or in a system can be called a nanoscale material. So these are other examples where you see these are like wires standing on a surface. These are very important for many electronic devices. Most electronic devices work through principles of emission of electrons. So emission will become very good if you have a pointed structure. That means an anisotropic structure, a rod-like structure, or a wire-like structure. These are a rod-like, wire-like. These are all like a structure which has a unique axis which has a special axis, which has the cross section very small, and the ejection of electron can be very good. So many field emitting devices use wires or rods which are in the nano dimension and which give rise to excellent properties. So nanowires have, or nanorods have excellent properties in devices, especially in sensing, in actuators, in solar cells, in transistors, in diodes, and as lasing materials, as lasers. So many of these structures are very important in applications in electronics, in electronic gadgets, say smart screens, smart televisions, mobile phones. Many of these have these kind of requirements where you will have these anisotropic nanostructures. When you have anisotropic nanostructures, there's another property which happens, which is called quantum confinement. Okay, it can be one-dimensional or two-dimensional, depending on the nanostructure. So if you have a wire, it means it is a one-dimensional structure, nanostructure, because there is only one dimension, which is in the nano scale. If you have, suppose, a square, which has 1 nanometer by 1 nanometer, but in the third dimension, it is 1 micron. So it forms a cuboid whose cross section is 1 nanometer by 1 nanometer, but the third direction is very large. It is 1 micron. Okay, then it will have a different kind of a confinement. Okay, so this can be a 2D material. So you will have wires, or we can have 2D nanostructures like graphene, which is a planar structure, and only it has got one sheet. A graphene has one sheet, but separated by others by a lot of distance. So in the two sheet, the dimensions can be very small. Of course, in graphene, the thickness is very small. Okay, so you can have a large area, but the thickness is very small. It is one atomic thickness. So there are different types of two-dimensional structures. So these are two-dimensional structures. Wires are one-dimensional structures. You can also, you might have heard of nano tubes. The carbon nanotubes are again one-dimensional structures. They are anisotropic structures. But you can also make what are called quantum wells, which are like you are trying to confine electrons within some regime where the potential energy has a minimum. Outside that well, the potential energy is maximum. So electrons can be confined. So there's a lot of physics, quantum mechanics in these nanoscaled materials, depending on what kind of structures that you made, one-dimensional, two-dimensional, or three-dimensional. Suppose you have a cube which has 1 nanometer by 1 nanometer by 1 nanometer. That means in all three dimensions, it is in the nano range, right? So it is a quantum, it is a nanostructured, 3D nanostructured material, because in all three dimensions, it has got a nano size. Okay, so you can have a 1D nano size, you can a nanomaterial, you can have a 2D nanomaterial, you can have a 3D nanomaterial. In biological materials also, you can have nano size. So you can have human cells, but of course they will be much larger. And you can put human cells on substrates, like you can put human cells on a silicon substrate, on silica, like PSI means porous silicon. This is a good substrate for many biological studies. You can put, for example, a bone cell on porous silicon. Many things. You can put proteins, enzymes, DNA, RNA, all these things can be put on surfaces and you can study them. You can do electrochemistry with them You can make an electrode after depositing DNA, RNA on a surface and do electrochemistry. You can do catalysis, you can do biocatalysis and study the properties.